product. You can get this for health food. And it's actually a sweetener that doesn't have any calories. Your gut can't digest it. So it tastes sweet, but you won't get any calories from it. If you have a little bit, it can make your food taste sweet. Have a little bit more, and it's an excellent laxative, so you don't want to push this too far. Nevertheless, it has a very low melting point, and so because this melts at such a low temperature, around 100 degrees centigrade, we don't need to use the water. And so we can use this as the liquid matrix to hold our fuel. So that's what we're going to do to mix up the fuel. 35 parts or 35 grams of this is where we're going to start. Wow, to the milligram. Now, because the sugar will melt, you really don't need to grind this up ahead of time because it's just going to liquefy. However, if you do grind it, it makes the pre-blending that I'm going to show you in a second work a lot better. So I'm going to take this little coffee grinder, and I'm going to add the 35 grams of the sorbitol, and we're going to give this a little bit of a grind. So a little bit of noise here for you headphone users. You only need a few seconds. It doesn't take very long. Now, we need 65 grams of an oxidizer, and typically you would use just potassium nitrate. However, if it turns out that you use a little bit of another oxidizer, you can improve the performance of the fuel because remember how I said in the other room how a rocket engine is a pressure engine. It's not just a heat engine. The heat creates the high pressure gas, but you need gas. And because potassium is effectively an alkali metal, if you use an oxidizer that itself contains nothing but gas, let's say, for example, ammonium nitrate, or you were to use ammonium perchlorate, this will actually increase the performance of the engine because we produce more gas molecules that can be exhausted out the back. In addition, if we use the ammonium nitrate, it will actually soften or melt around the temperature of the sorbitol and improves the viscosity. It actually makes it a little bit easier to pour. If you use too much of either of these supplements to replace some of that potassium nitrate, you will slow the burn down. You'll actually decrease the regression rate, so you don't want to go too far. And it turns out you don't need much because if you add just a few grams of this, you'll thin it out. And if you add a lot of grams to this, you'll not only thin it out and create a slowing of the reaction, but this is very hygroscopic. It will attract atmospheric water, and your fuel will get pasty and damp and sticky over time if you use a lot of this. So what I discovered is that by using 61 grams of the potassium nitrate and just 4 grams of the ammonium nitrate, you get a great mix that's thin, high performance, and it doesn't attract water. So that's what I'm going to mix up here, 61 plus 4. Now I'm going to take this blend and I'm going to grind it up in a different coffee grinder, keeping the oxidizer and the fuel apart. And we're going to bring this down to a much finer powder. Now the trick is we're going to take these two materials and we're going to pre-blend them before we hook up put it on the stove to cook it. So we're going to put the 65 grams of oxidizer in here, and we're going to put the 35 grams of fuel in here. And we're going to blend these things up by hand. It's a very easy way to do this. Just take a little plastic, rip it off, put a little rubber band around here like this, and then what we're going to do is just spin it around. Now, something you might notice here while I'm mixing this is I'm using cast iron. Now, the advantage of using cast iron is that it's a great pan, it's inexpensive, and it's nice because it distributes the heat from the burner so you don't get hot spots, but it also has a lot of thermal inertia. It's just heavy. And as a consequence, when we take this off the burner and we're filling the rocket, it doesn't cool quickly and then thicken up. And that's why I like using this for all the mixes. Now that this has been blended up, we're going to simply pour this into the pan, trying not to spill too much of it on the floor. And then we're just going to let it melt. As you can tell, I'm not using any water. In addition, because this melts at such a low temperature, I can actually use plastic spoons to do the distribution. They won't melt. It's kind of nice when you're working with rocket fuel that you're working at a lower temperature. It just seems like a good idea. Now, I like to use wood to mix this. Again, you could probably use metal, but I don't want to create any sparks, and it's cheap and disposable. And this has just the right curvature for my particular pot that it'll get into the grooves, and that's why I use these sticks for mixing. I've also used the spoons, but they're a little too pointy. So we're going to spread this out to distribute the heat over the fuel, and this will take a little bit of time. But eventually, you'll start to see the bottom become a little bit sticky as it's beginning to accumulate or gather some heat off of the pan. Now, a couple other warnings. This is an electric heater. You absolutely do not want to use flame when you're in contact with this. Now, as you can see, this has become very smooth, very creamy, and very low viscosity. But we can improve that even further by the other secret ingredient, and that is glycerin. If you use 1 cc of glycerin added to this, and you do that at the end, 2 to 1, this will thin out the mixture, doesn't seem to affect the burn at all, but makes it a little bit less viscous and easier to pour. And like I said, I'll try to be relatively neat, although you may get a little bit of spillage on the outside, but because this is water soluble, you can just wipe this down with a wet towel when you're done. Now, I don't know if you can see it because I'm using the guide to hold it. I'll try to do it above there so you can just sort of see how it pours, but I'll probably make a mess by doing that. But you can see it just dribbles in. And then actually, before I lose this fuel, I'm actually going to take what I have remnant here, and I'm going to put it on my aluminum foil. And that's for a little demonstration I'm going to do in just a little bit, so I want to do that before this gets too warm or too cool. And as you can see, the spoon is still intact. It's not melted. It's not softened. And this is very easy to clean out. You just rinse this in the sink, and you get a nice clean pan to work with. And if I can, I'm going to try to remove this liner. Oh, actually, let me see if I can show this to you. You can see how it got to the bottom. See what it looks like? I don't want to tip it too much so it pours over the side. But it's right to the bottom of the liner. And then if I grab the tube, which is actually quite hot now, it is about 100 degrees centigrade, and see if I can pull this out. Then I'll show you the tube again, show you that it stays nice and clean and has a nice level.
Do that again. Good.
Now what we're going to do is we're going to take advantage of the fact that because the fuel is soft, I'm going to take this and create the inner part of the grain. Now the problem is, even though this is polyethylene and it's very slippery, if you don't grease it, you end up with the fuel sticking to the outside. So the little trick that I've discovered that really makes this work nicely is you take a little bit, this glove is getting all sticky, let's go ahead and replace that, with a little bit of Vaseline. And because the fuel is water soluble, it won't dissolve the Vaseline off. So you just take a little fingerful of the Vaseline and smear it up real nice. Get it nice and greasy. Now you've got probably, almost 20 minutes, half an hour, before the fuel becomes too rigid that you're not able to put this in. But right now, it'll flow very nicely, and the level will rise as I do that. Now, I don't know if I can show you that. Maybe if I bring this over. Now, if I push this down, just like this, straight down to the bottom, it's viscous enough to stay vertical. And when this cools, we can just wiggle it, spin it a little bit, and we can pull this out, and we have a nice fuel grain. Now, we're going to do the same thing again, but we're actually going to build a larger motor. And the only difference between building smaller and larger, beside just more of everything, is it's easier. Because of the scale of everything, it's just easier to get the fuel in and it's easier to fit things. So you're going to find that this, as you get better at this, you're actually going to find that it gets easier and easier. Now, one of the things that you'll find at Rocket Motor Parts is that they're limited somewhat in the choices that they have in the larger rocket engines for nozzles. And so therefore, rather than the small nozzles, which are about $3 each that I'm using for these motors, you can't really buy the larger motors, the larger nozzles made for the 38 millimeter tubes. And so what I did is I actually bought a rod of graphite and I machined these nozzles myself. And it's nice having a lathe because you can put. And unlike Ben over at Applied Science, who found that working with graphite was very, very, discovered that as long as you keep the velocity way, way down, you don't move this stuff up into the atmosphere, just sort of, and by just using a vacuum, careful to keep your velocities down, this was, and although this is reported to be some want to use carbide tools, tungsten carbide, I found that after 5 or 6 nozzles, the flawless. So you can probably produce a lot of nozzles. And the other thing is that it is extremely to heat in a non-oxidized, and as I described before, we're kind of compelled to be there simply because of the so this is almost impossible to melt, to make. It's relatively inexpensive. I did a pretty good job. Anyway, the other issue is that the liner that tubes for, online or a car, you can't find one that fits very well here. So I ended up turning down a thin-walled aluminum tube with a little retaining plate. And so in order to keep the fuel to the right level, I ended up using this aluminum liner to protect the upper end of the tube when we fabricate this. In addition, I can't find the right size epoxy nozzles for the core forming. And so I just got a thick wall plastic tube, and this is made out of Delrin, and it's very inexpensive, probably about $3. And then what I did is I ground the other end, the one end of this, to make it a little bit pointy, and then got a very loose fit aluminum rod that fits in the end of this very loosely. And then with a drill stop here, just insert it all the way down, and you end up with a nice pointy plunger that you can push into the fuel. And greasing this up, we're going to use this to form the core inside of this larger engine. Now, larger engine, more fuel. More fuel, I have to go to a different scale because simply my other scale only goes up to 50 grams. So we're going to get our pot, a bigger pot now, and these come with nice little, what do you call it, spouts, that allows you to actually literally pour the fuel right in, so it makes it very easy to work with. So we're going to measure out 2.4 times as much fuel. We're going to make 240 grams for this motor, and so that means we're going to need to use 84 grams of the sorbitol. So now I have 84 grams of the sorbitol. We're going to put it in the sorbitol coffee grinder. Now we're going to need 156 grams of oxidizer, or 146 grams of the potassium nitrate and 10 grams of the ammonium nitrate. All right, we now have 156 grams of oxidizer, so we're going to put this in the oxidizer coffee grinder. Yeah, it's starting to warm up in there. Now, I'm going to come over here. I'll bring this actually where this was. And if you look at this, you can see, if you touch it, that it still moves. Now I'm going to just play with this a little bit just to make sure that this is going to work. And we're just going to kind of ooze it out of the hole, nice and slow. Seems to be coming pretty well. There. That's what you get when you use the Vaseline. It's nicer. And if you look in the bottom of the rocket, you can see
a little bit up.
A nice grain. And now what we're going to do is, because we want to fill this With the epoxy, what we're going to end up doing is I'm going to use some RTV. This is a rubber. And I'm going to put a little bead around the outside of this in order to form a seal so that when I put the nozzle down, the epoxy doesn't drip around the nozzle and get into the central hole. So I'm going to move this closer to the camera that we're using from above, just to get an idea of how much I put in here. This isn't really critical because it's not in any way structural. All this is going to do is just form a layer, sort of a gasket around the edge. So the epoxy, which is doing all the work, and again, this is kind of hard to do for the camera. Can you see this? Mm-hmm. Okay. Now, I did a much neater job when I was doing this all alone. And this is a little copious. You don't need to use quite that much. I just had some challenge trying to do this as I'm holding this for the camera. But you want a nice little O-ring looking type of gasket there. And then while this is still liquid, what we're going to do is we're going to insert the nozzle into here until it stops pushing in. Right about there. Now, what we're going to do is we're going to let that again dry for 3 or 4 hours, and then we can feed our epoxy in there in order to get a very nice seal around the edge. But you don't want to try to use this as it's still kind of liquid as a sealant. But you don't have to wait hours and hours and hours and hours. You could probably do this in about 2 or 3 hours. But except for the different parts that I'm using, different core, different guide, the process is the same. And you could obviously keep scaling this up even to much larger tubes. They make and will sell you these spiral round tubes up to 100 millimeters in diameter and about, so you could make truly massive rocket engines. And I'm not so sure that you'd really want something that big for anything that you use outside of Black Rock or, you know, some protected zone, even for testing. But it's nice to know that you could. All right, so you can see now that it's a very creamy mixture with about the same viscosity as the smaller volumes. Turn off the heat. Once you get to that point, you don't gain anything by increasing the temperature. It really doesn't get any thinner. And I'm going to add 2.4 milliliters of the glycerol. Now, if you add even more glycerol, it will get even thinner. But what I found is that the fuel will actually get softer when it finally hardens up. And you don't want a soft fuel grain that could collapse under the load of acceleration or vibration. However, I tested in our centrifuge some samples of the grains, actually with the core cut in them in a large 50 milliliter centrifuge tube. And it was able to withstand 150 Gs for a couple of minutes without any kind of collapse. Now, if you look over here, I'm going to move this over so you can see this. And I am left-handed, so you won't see the inside of the pot, but you'll see what happens when I start to pour this. You can see that I'm right to the bottom of the aluminum ring.
Do that again.
I'm going to try to do this without pouring it into the ring.
Good.
Okay. And then what we're going to do, before this gets any thicker, is I'm just going to extract the ring. And now I'll hold this down again so you can see the result.
Good point.
You can see how clean it is, and you can see it's nice and flat. And it's at the correct level. So then what we're going to do is I'm going to give this a couple of minutes to cool down because it's really low viscosity right now. And then I'm going to grease up my rod. We'll insert it in there, and we'll give it a little bit of time to cool. So I'm going to go ahead and just steadily put this right down the middle. So it raises, in this case, raises about 1.5 centimeters. And so what's going to happen is once we let that cool a little bit more, then I'm going to pull this out, and then we're going to be able to gasket this just like the other rocket motor. Now I want to talk to you about regression rate. One of the things that's nice to be able to control with your engines is to be able to control how fast the burn occurs. And if you're using this typical mixture, there's not too much you can do other than maybe try to tweak the fuel in the oxidizer a little bit. But there's a much more powerful technique that you can use, and that's by using a catalyst. It's the same purpose for sulfur in gunpowder. And so what you can do is by adding to that 100-gram mix that I described before, which is 65 of oxidizer and 35 of fuel, you can add a single gram of iron oxide. Now, this is micron scale particles, a couple of microns across, and it's very easily obtained from pyrotechnic supply houses like Skylighter, which is a supplier for a lot of our chemicals. And these grains do not get consumed. This is not like in thermite. This basically is just an iron oxide surface that acts to speed up the decomposition of the oxidizer into free oxygen so it can burn more quickly. So as little as 1% of these granules, and if you had nanoparticles, you could use maybe 0.1%, which is what they use in the larger rocket engines like for the space shuttle. But nevertheless, just 1%, so 1 gram to 100-gram mix of this added to the standard mixture is going to produce a much faster regression rate. So let me mix up some of that and I'll show it to you. I'm going to start out with the sorbitol. Now you can trust me on the measurements. I'm putting in 35 grams, so I don't know that we necessarily have to see the actual measurement in front of us. Be careful with this stuff. It stains everything. It's a large particle, so it doesn't really get into the air, but when it gets on surfaces, it's a wonderful red dye and actually makes your fuel very pretty. So we just want a single gram of this. Now we're going to put this in the grinder. Now, while I have you here, I think we're probably close enough that what I'm going to go ahead and do is I'm going to go ahead and get the rod out of the larger motor before it gets too cool. So now I'm going to extract this, and the trick to doing this is we're going to get the center rod out. Now I have an airflow that allows me to get the rod out without sucking the material back into the space that I'm forming here. So we'll do this rotation to break up any holes or defects. Pull this guy out. Nice. I mean, there's not much debris on here. And you can see inside, formed a pretty good grain in here. Good depth. It's a little bit oblong at the top because I wiggled. But if you wait a little bit longer, you probably wouldn't even get that defect in there, but it's a very smooth hole. So then the next step, I'm going to put on the gasket material here. Nobody's perfect, but it still serves the purpose. A little junky looking, and you can see how the gasket material is around the outer edges. And then what I do is I will press the rocket engine into here until it reaches a stop. That spreads out the gasket material, make sure that I have a good seal. Now, what happens if you actually want to slow the rate of the rocket burn down? Now, why would you ever want to do that? Ever heard when they were launching the big rockets, like say the space shuttle, that when they ignited the boosters and began to accelerate it upward, what would happen is you needed to get away from the Earth's gravity. It's always a taxation that you're paying because you have to first lift the rocket before you can get it up and accelerate it. And so they want all the power they can initially. But then eventually what happens is as the rocket gets going faster and faster in the lower atmosphere, you develop a lot of aerodynamic resistance, and that produces a lot of structural load on the rocket. And so what they'll do is they will throttle back once they get to close to around Mach 1. And the idea being that we'll get through the lower atmosphere at a reasonable level of rate of rise, and we'll accelerate very slowly. And then once we get to the thinner air, we then want to throttle up. That's actually when the Challenger disaster happened, was when they went to 100% throttle. It had nothing to do with the main engines, but it was just at that time if you listen to the recordings, that the disaster occurred. Nevertheless, you can't really do that with solid rockets. All you can do is either use different rockets or additional rockets or multiple stages that have more or less rockets in each stage. But there's another application, and that is if you wanted to build a rocket engine that was not made to just thrust as fast as you can. You're not building an RPG, you're not trying to boost something up in 1 second, and you're worried about the structural loads. You might say for gliders, be able to take a large glider and rather than putting an E-motor on it or being able to try to toss it off of a ridge, you could put a small rocket engine on it that would have a relatively low thrust for a long period of time, 10, 20, 30 seconds. And in order to do that, you want a very small aperture nozzle, much smaller than the ones that we've been using, and you want a much lower rate of burn, regression rate. The way to do that, as I described before, is changing the oxidizers. So rather than speed it up by adding a catalyst, we're actually going to slow it down by adding more of a different oxidizer, specifically ammonium perchlorate. So in the original mix, we used 65 grams of oxidizer, 61 of the potassium nitrate, 4 of the ammonium nitrate. In this case, what we're going to do is we're going to use 65 grams of oxidizer, but we're going to make 15 grams of that ammonium perchlorate. Otherwise, it's an identical mixture to the first mixture we made up. We're just changing the oxidizer ratios a little bit, and you'll see what happens when we demonstrate this. So let's go ahead and make up a mixture of that. So we're going to start out with 35 grams again of the sorbitol. So 35 grams of sorbitol into the sugar grinder. Now we're going to be doing the oxidizer. And in this case, instead of doing 61 and 4, we're going to replace part of that 61 with the ammonium perchlorate. But I think we're going to start with the potassium nitrate. Now the ammonium perchlorate, we want 15 grams of this. And then finally, don't forget, the ammonium nitrate, 4 grams of this, to bring us up to 65. Put the oxidizer in our mixing, blending beaker, and our sorbitol. Same routine. And we'll add this. Okay, so now what we're going to do is I'm going to add the glycerol, 1 cc. That's pretty similar. So those are pretty similar in size. I'm going to let this cool over here. And then while these are cooling, what I'm going to do is I'm going to go ahead and show you how to finish up these rocket engines. They've had enough time that the gasket material has firmed up. And so what we're going to do is I'm going to mix up some epoxy and we're going to inject it into the gap. So I'm going to start out with one of my cups and we're going to mix up that standard mix of 25 and 15. Now that this is mixed, we're going to draw this up in a syringe, and similar to what we did when we built the bottom, we're going to fill this up using a short industrial non-beveled needle to do the epoxying. And so I'm going to put this down here very carefully and all the way to the bottom so I don't trap air. And then I'm going to inject the epoxy and let it sort of slowly rise and spread around the periphery, so I don't trap any air. That's pretty good. Now if I can carefully bring this over, you'll be able to see. I could probably put another 0.5 milliliter in there, but basically you get the idea. So what I'm going to do now is I'll fill the bigger motor, same idea, and it's easier. Again, everything is easier the bigger you get. So bring this over here like this. I'll finish up this syringe and then we're going to add some more. This is going to need a lot more. So then you just insert this down to the level of the epoxy so that, again, you're not trapping bubbles. And as you inject it, you'll see that it flows around the edges, around the sides. Moving the needle just speeds the process, but it's strictly not necessary. That's pretty much it. So then we just let that cure, and by tomorrow we have a very hard epoxy-based ring that will retain the nozzle, and this motor is done. Finally, ways to ignite it. You can use an E-match or an electric resistance element that basically burns and starts off a pyrotechnic mixture, or you can use a fuse. And if you're just starting out, a fuse might be the easiest way to do this. Now, there's a bunch of different types of fuses. There's rapid and slow burning fuses. There are what are called cannon fuses. This is a type of fuse where the burn stays inside of the tube. It doesn't produce a lot of heat outside of it. You don't want to use that. This is a very typical type of fuse. It burns at a rate of about 1 centimeter a second or about 1/2 inch a second, produces a pretty hot flame, and I found with my engines pretty reliably will start the engine by simply inserting this to the bottom of the central core and lighting it. But if you want to enhance the performance, you can make the fuse a little hotter by adding to it a little bit of a fast-burning fuse. This is a very hot white fuse, and this will burn in about 1/4 of a second. And simply by tying these together with a little bit of thread, a little nylon thread, this is small enough to be able to fit in the nozzle and will add additional heat without having to do anything chemical. Now, that's nice, but if you have a very narrow nozzle, you might not be able to get this in here, and it does take a little bit of time. And so another thing that you might do, especially if you're going to make a lot of them, is you might enhance the properties of the fuse by adding some hot-burning pyrotechnic flash powder to the outside. The trick to doing that is actually very simple. Get some contact cement or even PVC cement will work. And you simply take a length of fuse that will be convenient to insert into the motor and have enough so you can run. And so I took these little 20 centimeter, 7-inch length of fuse, cut it, and then I marked it about the depth that it would have to go into the engine. And then simply taking this contact cement, you dip it in to the mark and pull it out. Now, if you wait a few seconds, what will happen is this will begin to drip off, and then after about 5 or 10 minutes, it will stiffen up enough that it's not going to run anywhere. And what you'll end up doing is you'll end up producing a very sticky, rubbery surface as the solvent dissolves, and this then can adhere to the flash powder. Now, the flash powder is a very simple mixture. I'm not going to mix it up for you because it's really simple. It's a 50-50 by weight mixture of aluminum powder and ammonium perchlorate. That's it. You blend it up. You can do it by weight. You blend it up into a little cup, and this powder then will stick to the outside of the wick and form that extra additional heat that you're going to want during the process. Now, I'm rushing this a little bit. I'd let this sit normally for a couple of minutes. But if you simply take the powder in a tall cup like this and just jam the wick in here, you can roll it around. Nothing neat about this. But what will happen is it will attach to the surface and then just flick off the extra like this and set this in another cup and let it dry. Let it dry overnight. It'll be fine. That's what I did to these wicks here. Now, at least you think this little tiny layer isn't going to make a difference. Let me show you how powerful this mixture is. I'm going to take a very small quantity of this flash powder, and I'm going to go over behind me onto this fire brick here. And I'm going to take a small quantity of the flash powder. That's not a small quantity. Not very much.